Right. So this chapter is about nuclei, what is present inside a nucleus, and what is the use of a nucleus basically. Okay, to us, I mean, how can we extract energy from it? Okay, or and how they behave is what we are going to study. Now, from Rutherford's alpha ray scattering experiment, okay, it was discovered that all the positive charge in an atom, okay, lies at its center in a very small volume called the nucleus. So that positively charged space in an atom is called nucleus. Fine. And the positive charge that is inside a nucleus is a multiple, okay, of the elemental charge. We know the elemental charge is the charge of an electron, minus 1.6 into 10 power minus 19 coulombs. The positive charge that is present, okay, in matter is basically a multiple of plus 1.6 into 10 power minus 19 coulombs. So the total charge in a nucleus should be an integral multiple of plus 1.6 or 1.602 into 10 to the power of minus 19 coulombs. Okay, so this basic particle, which has a charge of 1.602 into 10 power minus 19 coulombs, is what we call as a proton. Fine. So the charge of any nucleus, the net charge of any nucleus, is an integral multiple of this. So it's an integral multiple of the charge of the proton. Fine. But it was discovered that there were some nuclei which have the same amount of charge but different amount of mass. Okay. Now, if two different nuclei have the same amount of charge, it means they have the same number of protons. Fine. Maybe two protons or three protons, whatever it is. If the charges of two nuclei are equal, okay, let's call them as X and Y. Total charge of X is same as total charge of Y. That means the number of protons in X should be equal to number of protons in Y. Okay. But the mass of X is not equal to mass of Y. Now, if the charge is same, it means the proton number is same, but masses are not same. It means there is something else in the nucleus, not just the protons. Okay, and that something else is not the same for both these nuclei. And that something else should be neutral mass, uncharged mass. Fine. So later, the scientist Chadwick, fine, based on experiments on nuclei. Okay, basically what he did is he made alpha particles bombard with nuclei. So basically he kind of broke open nuclei by making high energy alpha particles collide with them. Chadwick discovered the existence of neutrons. Okay, he discovered that there is some neutral mass coming out of the nucleus when you break it open. Okay, so he discovered the existence of neutrons, and now we know that nuclei consist protons and neutrons. Okay, there is one nucleus, the nucleus of hydrogen atom, which only consists of proton. It doesn't have neutrons. All other nuclei have neutrons in them. Fine. So basically nucleus is a space which consists protons and neutrons. See, later on it was discovered that there are some other particles also present inside the nucleus, but for now, as far as your syllabus is concerned, we'll stick to only protons and neutrons. Fine. So the number of protons in a nucleus is denoted by the symbol Z. We call it as the atomic number. And the number of protons plus neutrons in a nucleus is denoted by the symbol A. We call it as the mass number. Fine. So the standard notation for a nucleus is Z, X, A. Z indicates atomic number, A indicates mass number. Now we just discussed that there are nuclei which have the same number of protons but different masses. Okay, If the proton number is same, the mass contributed by the proton should be same, but their overall mass is different, means the mass contributed by the neutrons is different, means the number of neutrons is different. Okay. Now, if proton number is same, atomic number will be same, but neutron number is different, then the mass number will be different. Okay. So nuclei having the same atomic number but different mass number. Okay. You can take it like this: ZXA as one of them, and or ZXA1 and ZXA2. Atomic numbers are equal, mass numbers are different. Can one of you tell me what are such nuclei called?
Isotopes.
Isotopes. Okay. And it was found that every element in nature has isotopes, including hydrogen. Hydrogen has 3 different isotopes. Fine. Okay. Now, if the proton number is same, atomic number is same, neutron number different, mass number different, they are called isotopes. If the proton number or the atomic number is same, then it means the element is same. The chemical properties will be same. That's why we use the same symbol to represent the element. Fine. Now, for every element, we assign something called an atomic mass. Okay. The average mass of an atom of that element is what we call as its atomic mass. Now, masses of atoms and nuclei are very, very, very small compared to the regular units of mass that we use, grams, kilograms. Compared to that, the masses of atoms and nuclei are very, very small. Okay. So to express these small masses, like masses of atoms or nuclei, we use another unit of mass called the atomic mass unit. AMU, or sometimes just denoted by the symbol U. Can any of you tell me the definition of one atomic mass unit? Like which mass is taken as atomic mass unit? Basically, it is 1/12 the mass of a C12 atom. Okay, I should say C12 nucleus. Okay, this is what we call as one atomic mass unit. And how much is it? It is close to 1.66 into 10 to the power of minus 27 kg. Okay, this is what we call as an atomic mass unit. And to express the masses of atoms, protons, neutrons, nuclei, okay, this is a convenient unit. Fine. Now, the mass of a proton, you don't have to remember these values. If necessary, they'll give you these values in the question paper. But just remember how small they actually are. Okay. The mass of a proton is close to 1.0073 atomic mass units. Now, atomic mass unit is this much, 1.6 in 10 power minus 27 kg. Mass of a proton is close to this value. 1.0073 is almost equal to 1. So, 1 atomic mass unit, you can say. Okay, but there is a small difference, not exactly 1 atomic mass unit. Next, the mass of a neutron is 1. Just a moment. Okay, 1.0087 atomic mass units. So what you need to remember is that mass of a proton and mass of a neutron are almost equal, but neutron is the heavier one. Okay, there is a slight difference, and in this chapter that difference matters. Okay, because we'll be doing calculations based on these exact masses. So proton mass, neutron mass are almost same, like till the last chapter, when we solve problems based on proton and alpha particle accelerated by a certain potential difference and all, we used to assume their masses, proton mass, neutron mass, to be same. Okay, so for those calculations, it is safe to assume that their masses are same. But when you need to calculate nuclear energy, okay, how much energy a nucleus can release, or nuclear binding energy, you need to consider their exact masses. So remember that neutron is a slightly heavier particle than a proton. Okay. Fine. Yeah. So we were discussing about isotopes. Basically, nuclei of the same element which have different number of neutrons. So their mass numbers will be different. Now, for every element, we assign something called an atomic mass. Okay. Or you sometimes you call it atomic weight also. Now, if an element has isotopes, how do we assign an atomic mass? For example, can one of you tell me how much is the atomic mass of hydrogen? Generally, what is the atomic weight of hydrogen in calculations that you do in chemistry?
1.
1 watt. Okay. You say it is 1 gram per mole. Okay. 1 mole of hydrogen atoms, they weigh 1 gram. Fine. And what about the atomic mass of carbon?
Six gram.
It is not 6. Atomic number is 6. Atomic mass of carbon is not 6. Okay. It is close to
Oh,
12
sir,
grams.
it's 12.
Close to 12 grams per mole. Okay. Not exactly 12, but it's close to 12 gram per mole. But if speaking in atomic mass units, atomic mass of hydrogen is approximately equal to 1 AMU or 1 U. Let's write it as 1 U, 1 atomic mass unit. And that of carbon is close to 12 atomic mass units. Fine. What about chlorine?
35.
35.5. Okay. Chlorine's atomic weight is 35.5. So now see, if a nucleus, or let's talk about atom itself. Atom consists protons, neutrons, electrons. Electron mass is very small compared to those of protons or neutrons. Okay, it is about 1 by 10,000. So if there are a few electrons in the atom also, it's not going to cause much variation in the mass of an atom compared to its nucleus. So mass of atom is almost equal to the mass of nucleus. Fine. Even in atomic mass units, if you express, the mass of atom is almost equal to the mass of a nucleus, because electron mass is that small. It is very small compared to AMU also. Okay. Now, if atoms consisted, if nuclei consisted, nuclei do consist protons and neutrons only. Now, proton mass, neutron mass is slightly different. Let it be. Now, chlorine has how many protons? Atomic number of chlorine is how much? 17. 17. So it will have 17 protons. Fine. So those protons will contribute 17 times of this mass. And the rest are neutrons. The neutrons will contribute. Okay, chlorine's mass number, I think. Okay, if you take it as 35, then there should be 17 protons and 18 neutrons. Right? 17 protons will contribute mass of 17 into 1.0073 atomic mass units. 18 neutrons will contribute a mass of 18 into 1.0087 atomic mass units. You multiply these two, the number still doesn't become 35.5. Okay, it will be 35.00 something. It won't become 35.5. Okay, but why is the atomic mass of chlorine taken as 35.5 then? Because chlorine has isotopes. Not just chlorine, every element has isotopes. Now, if you consider Cl35, okay, 17 Cl35, you're only considering one of the isotopes of chlorine, fine, which has 17 protons and 18 neutrons. Its mass will be 35.00 something. But there are other isotopes of chlorine as well. Okay, so when we assign atomic mass to an element, be it hydrogen, carbon, chlorine, nitrogen, whatever it is, when we assign atomic mass to an element, okay, we basically average the atomic masses of all isotopes of that element. It's not just one isotope's mass that we consider. Okay. Now, hydrogen has three isotopes. One of them is 1H1, the other is 1D2, deuterium. Okay. The other is tritium, 1T3. All of them have one proton only. Hydrogen has no neutrons. Okay. The hydrogen nucleus has no neutrons. Deuterium nucleus has one neutron. Tritium nucleus has two neutrons. Okay. Now, when you assign atomic mass to hydrogen, you have to average the masses of these three entities. Okay. And by averaging, we don't just mean mathematical average. We have to take, we don't mean direct average. We have to take a weighted average. We have to give weightage to these uh, isotopes. And what weightage do we assign? We assign weightage based on their abundance in nature. How much of, uh, I mean, in terms of percentage, how much percentage exists in the form of 1H1? How much percentage exists in the form of 1D2? How much percentage exists in the form of 1T3? Those percentage abundances are the weightages that you assign. Okay. For example, okay, just an example. I'm not taking exact values. Just as an example, let's assume 99% of all the hydrogen available is in the form of 1H1, okay, in nature. And let's say 0.5% is in this form and 0.5% is in this form. Now, if you want to assign an atomic mass to this element called hydrogen, you will have to average you will have to take the weighted average of the masses of these three isotopes. Now, mass of 1H1, it's just the mass of a proton. Fine. Mass of 1D2 is mass of proton plus mass of neutron. It has one neutron. Okay. Mass of 1T3 is mass of proton plus 2 times the mass of neutron. Fine. Actually, there is slight variation between the actual nucleus mass and the sum of masses of protons and neutrons also. We'll discuss that. We'll talk about something called mass defect. For now, let us roughly consider it like this. Okay. So the mass of 1H1 is close to 1 atomic mass unit. Mass of 1D2 is close to 2 atomic mass units. And mass of 1T3 is close to 3 atomic mass units. Now 1 to 3 average is 2. But that is not how you are supposed to average and find out the atomic mass of an element. In the form 1H1, it exists 99% of the times. So 1 into 99. Plus, in the form 1D2, it exists 0.5% of the times. So 2 into 0.5 plus in the form 1T3, it exists, let's say, 0.5% of the time. These are just some rough values that I took and not the actual percentage abundances. Divide by 100. This is what you call as the atomic mass of hydrogen, or this is what you assign as the atomic mass of the element hydrogen. And not just for hydrogen, for any element, this is how the atomic masses are assigned. You need to know what is the percentage abundance of isotopes of that element. Okay, and then you average this will be close to 1 atomic mass unit, slightly greater than that. Okay, so we say that is the atomic mass of hydrogen. Okay, let's consider another example. Let's say there is an element whose, this is just a rough example, not an actual one. Let's say there is an element whose atomic number is 20 and assume it has 3 isotopes. First isotope, let's say the mass number is 40. Second isotope, okay, let's just take 2 isotopes, 42. And their percentage abundances in nature are like this. In 20x40 form, let's say it exists 80% of the time, or it is found 80% of the time, or 80% of this element available in nature is in this form, and the other 20% is in this form. Okay. Calculate the average atomic mass of this element. Now for 20x40 means there are 40 nucleons. The sum of protons plus neutrons is 40. So 20x 40, that nucleus's mass can be taken as 40 atomic mass units. 20x 42, that nucleus's mass is close to 42 atomic mass units. Okay. But in one form it is found 80% of the time, in the other form it is 20% of the time. Calculate the average atomic mass. It will be some value between 40 and 42. Do this both of you, I'll give you 2 minutes. Any answer? See, the nucleus 20x 40 has a mass of 40 atomic mass units. 20x 42 has a mass of 42 atomic mass units. And you are given their percentage abundance. You just have to find out the weighted average of these two numbers. Okay, weighted average of 40 and 42. The weightage you give to 40 is 80 and the weightage you give to 42 is 20. So the average atomic mass can be calculated as 40 into 80 plus 42 into 20 divided by 100 atomic mass units. That's all. 40 into 80, 3200 divided by 100 becomes, sorry, 8 4 is 32, right? 32 divided by 100, so becomes 32 plus 42 into 42 into 2 is 84 into 10, 840 divided by 100 is 8.4. 32 plus 8.4 becomes 40.4 atomic mass units. So that's the atomic mass we will assign to this element X. So this is how atomic masses are assigned to elements. You have to consider the masses of all their isotopes and their relative abundance in nature. Is this clear to both of you? Any doubts in this? Fine. Right. So nuclei, they consist protons and neutrons. This is how you find out the mass. We have discussed the mass of proton, mass of neutron. Then this is how you assign the atomic mass to an element. Generally, you assign atomic masses like this. Next is the size of a nucleus. Now, nuclei consists protons and neutrons. Okay, then the size of a nucleus should depend on how many protons and neutrons are there in it. And the sum of the number of protons and neutrons together is what we call as the mass number. Okay, protons, neutrons together are called nucleons. Basically, constituents of the nucleus. They're called nucleons. And the size of the nucleus should depend on the number of nucleons. So it depends on the mass number. Nucleus is roughly a sphere. Okay, any nucleus is roughly a sphere. So we can talk in terms of radius of the sphere. And radius of any nucleus is equal to R naught. Okay, that's a constant value multiplied with A. A is the mass number to the power 1 by 3. Okay, now see, if there are a number of nucleons, and let's say each nucleon has a certain volume, okay, then the total volume of the nucleus should be a multiple of the volume of each nucleon. Okay, so volume wise, it will be proportional to number of nucleons. Radius wise, it will be proportional to number of nucleons to the power 1 by 3. So you can consider that also. Volume of a nucleus should be proportional to the number of nucleons. Okay, and it's a sphere. No, volume of a sphere, is 4 by 3 pi r cube. Okay, so if you take power 1 by 3 on both sides, you can say radius will be proportional to a power 1 by 3. Okay, and this value r naught, which is basically a proportionality constant, how much will it be? Just a moment. R naught is 1.2 into 10 to the power of minus 15 meters. Very, very small distance. Uh, 10 power minus 15, what is that factor called? Like 10 power minus 3 is milli, 10 power minus 6 is micro, 10 power minus 9 is nano. What is 10 power minus 15 called? Okay, 10 power minus 9 is nano, 10 power minus 12 is pico, 10 power minus 15 is femto. So you can call this as femtometer, and this has a separate name given to it. It's called Fermi. Okay, so R naught you can say is 1.2 Fermi. Like some of these units are given a separate name. 10 power minus 6 meters, you call it as a micrometer, but it has been given a separate name also. It's called a micron. Fine. Similarly, 10 power minus 15 meter, you call it as a Fermi. So the value of R naught is that much. Therefore, the usual radii of nucleus or nuclei will be in this order: 1.2 into 10 power minus 15 multiplied with a power 1 by 3. It depends on the mass number as well. Okay. Uh, Questions based on this are quite common. They'll give you two nuclei. They'll give you the mass numbers of two nuclei and ask you what is the ratio of their radii. They can ask you what is the ratio of their volumes also. Okay, if you know radius, you can tell the volume of a nucleus. Nucleus is considered to be a sphere, then you can say the volume is equal to 4 by 3 pi cube of the radius becomes R naught cube multiplied with A. Okay, we know volume should be proportional to the mass number. Okay, number of nucleons that are present in it. The proportionality constant is 4 by 3 pi R naught cube. Okay. Now, volume of a nucleus depends on mass number in this manner, and the mass of a nucleus also depends on its mass number of nucleons, how many protons and neutrons are there. And proton mass, neutron mass are almost equal to 1 AMU. Then mass of a nucleus can be taken as A atomic mass units. Okay, A is the number of protons plus neutrons. So you can assume together the mass will be A atomic mass units. Then the density of a nucleus, which is mass by volume. Mass is A atomic mass units, close to that, divided by, okay, or leave the unit. Mass is proportional to mass is proportional to mass number. The volume is also proportional to mass number. Fine. You substitute these two values. Now, A atomic mass unit. So the numerator is in atomic mass units. Atomic mass unit is 1.66 into 10 power minus 27 kg. Okay. Now A gets cancelled. R naught we just discussed. It is 1.2 into 10 power minus 15. When you cube it, R naught cube becomes 1.2 whole cube. 1.2 whole cube is approximately how much? Okay, 1.73. So 1.73 into 10 power minus 15. When you cube it becomes 10 power minus 45. So when you try to express the density of a nucleus in SI units, this is what you get. Send the 10 power minus 45 to the numerator. Numerator becomes 10 power 45 and minus 27. 45, 27, there is a difference of 18. Fine. So the density of a nucleus is close to 10 to the power of 18 kg per meter cube. In SI units, it is this much. This is extremely high density. Okay. And you can see that the density of a nucleus will be independent of its mass number. Means means all the nuclei that are found in nature have almost the same density. Okay. So radii of nuclei will be different depending on their mass number. Volumes of nuclei will be different depending on the mass number. Masses of nuclei will be different depending on the mass number, but their densities will be the same. Okay. And nucleus is an extremely dense space, you can say. Fine. You know that in an atom, most of the space is empty. By most, we mean in terms of volume, 1 by 10, 1 by 10 power 15 is the fraction occupied by the nucleus, is the fraction of volume of an atom occupied by the nucleus. The remaining, uh, how do you say? See, 1 by 10 power 15 volume belongs to the nucleus in an atom. The remaining volume, 1 minus 1 by 10 power 15, that is the fraction of volume which is empty. Fine. So whatever mass of the atom is present in this small fraction of the volume. Okay, that is why it is very dense. Fine. Atom as a whole is not that dense. Okay, the matter that we find in daily life is not that dense. Okay, but nucleus, if you see, it is extremely dense, 10 power 18 kg per meter cube approximately. And remember this point, all the nuclei found in nature have almost the same density. Okay. Next, mass defect and binding energy of a nucleus. Very important. Now, nuclei consists protons and neutrons. Now, for example, you take the nucleus ZXA. Okay. The number of protons in this is Z. The number of neutrons in this is A minus Z. Now, if it consists protons and neutrons, we expect the mass of this nucleus ZXA to be equal to Z times the mass of a proton plus A minus Z times the mass of a neutron, because those many protons and those many neutrons are present. So we expect the mass of the nucleus to be the sum of mass of number of protons that are there and the sum of mass of number of neutrons that are there. But it is found that the mass of a nucleus is always less than the sum of masses of protons and neutrons added together. Okay, experimentally it has been determined. See, basically this is what we expect, but this is not what happens. This is not what is observed. The mass of a nucleus ZXA is always found to be less than the sum of masses of individual constituents. Z times the mass of a proton plus A minus Z times the mass of a neutron. This difference in masses, okay, when you add the masses of protons and neutrons separately and you find out the mass of the nucleus, okay, there will be a difference. That difference in masses is what you call as the mass defect of a nucleus. Delta M. So you can calculate it this way. So protons and neutrons, when their masses are added separately, that sum will be greater than the mass of the nucleus. Okay. So Z times the mass of a proton plus A minus Z times the mass of a neutron. This sum minus the actual mass of the nucleus. So the mass of ZXA. This difference is what we call as mass defect of a nucleus. Right? It will be a small value only, but it will be non-zero. For all nuclei, it is non-zero, except obviously for hydrogen. Hydrogen has only one proton, so you can't expect mass defect in a hydrogen nucleus. All other nuclei, which have protons and neutrons together, will have non-zero value of mass defect. Okay. Now, how do we explain this? If nucleus consisted protons, neutrons, Z number of protons and A minus Z number of neutrons, then the mass of the nucleus should be equal to sum of the masses of Z protons and sum of the masses of A minus Z neutrons. Or if there was something extra in the nucleus, then the mass of the nucleus should have been more than this sum. Okay, how can it be less? This is where Einstein's mass energy equivalence comes into play. Now, inside the nucleus, protons and neutrons are held together. Fine. And nucleus is a, what can you say? It's a stable particle. A nucleus doesn't disintegrate on its own. Fine. The protons and neutrons which are there inside the nucleus are staying there happily. They are stable. Fine. In fact, to bring them out, you need to supply energy. To separate the protons and neutrons of a nucleus, you have to supply energy. Means the protons and neutrons, when they are inside the nucleus, are more stable compared to when they are outside. Okay, you consider it like this. Let's say protons are denoted by these green dots and neutrons are denoted by yellow dots. So suppose the protons and neutrons are separate. When they are separate, their energy is high, or you can say higher, relatively higher on the whole, compared to when they are inside a nucleus. Right? So in the form of the nucleus, they have lower energy. How do we know this? To split open a nucleus, you have to supply energy. Means to separate the protons and neutrons, you have to supply energy. So nucleus needs to be given extra energy for the protons and neutrons to separate like this. Means in separate form, they have higher energy compared to when they are together inside the nucleus. And what did we just discuss? When you add their masses separately, the mass will be more compared to the mass of the nucleus. So separately, they have higher mass. Together, they have lower mass. So this shows us that there might be some relation between mass and energy. Lower mass, lower energy, higher mass, higher energy. Okay. So this is where Einstein's mass energy equivalence comes into play. And based on Einstein's mass energy equivalence, we can explain why the mass of the nucleus is less compared to sum of masses of individual constituents. Okay. Now, what is Einstein's mass energy equivalence? Basically, what Einstein proposed is that mass is also a form of energy. Okay, mass can be converted to energy, energy can be converted to mass. Okay, and how much energy can be extracted or how much energy is present in a mass m is given by this equation. E is equal to m c square, where m is the mass whose energy you want to calculate and c is the speed of light in vacuum, 3 into 10 power 8 meters per second, close to that value. Okay, so the energy corresponding to a mass m is calculated this way. E is equal to mc square. This is mass energy. This is not the kinetic energy of that mass, potential energy of that mass, or some other energy of that mass. The mass itself, if it is converted to energy, you can get this much energy from it. Okay, that is what is Einstein's mass energy equivalence. Right. So greater mass corresponds to greater amount of energy, lesser mass corresponds to lesser amount of energy. Now, based on this, we can explain why in the form of a nucleus, the mass is less compared to mass in the free form. Okay. So inside a nucleus, the protons and neutrons are stable. Okay. To separate them, we need to supply energy. How much energy needs to be supplied to separate the constituents of a nucleus? Okay. Or to separate all the protons and neutrons of a nucleus? The energy required to do that is what we call binding energy of a nucleus. Fine. So if you want to take them from this form to this form, if you want to make them separate from each other, okay, you will have to supply energy. And reverse, if you want to do the reverse, you will have to remove energy, but it's not easy to do the reverse. Anyway, so you supply energy, you can separate all the constituents of the nucleus. That energy is called binding energy of the nucleus. It varies from nucleus to nucleus, obviously. And how to calculate binding energy? Now we know that there is a difference in mass. Mass of the nucleus ZXA is less than the sum of masses of Z times the mass of a proton plus A minus Z times the mass of a neutron. Okay. Now corresponding to this mass, there will be one amount of energy. So energy in the form of nucleus, okay, energy of all the protons and neutrons put together when they are inside the nucleus will be the mass of the nucleus times c square. Whereas energy when they are separate will be Z times the mass of a proton plus A minus Z times the mass of a neutron times c square. Now you know E2 is greater than E1. That difference is the binding energy of the nucleus. Therefore, binding energy of a nucleus can be calculated as E2 minus E1, which is basically Z times mass of proton plus A minus Z times mass of neutron minus mass of the nucleus itself multiplied with c square. And this term is nothing but the mass defect of the nucleus. Okay. Therefore, binding energy of a nucleus is its mass defect multiplied with c square. And questions based on this are very common. They will give you the mass of a nucleus and they will give you separate masses of proton and neutron. Okay. Based on that, you will be expected to calculate its binding energy. But before we actually get into those calculations, there is something you need to know. Now, mass of proton, mass of neutron, or mass of nucleus itself, they are all expressed in atomic mass units conveniently. So they won't give you those masses in kgs. Fine. So suppose the masses of protons, neutrons, and the nucleus itself are given in atomic mass units, and you are expected to calculate the binding energy. You'll first find out the mass defect. If individual masses are in atomic mass units, okay, then you will get mass defect also in atomic mass units. You can't multiply mass defect in atomic mass units with speed of light in SI units and expect to get an answer for binding energy. Okay, I mean, you will get an answer, but the unit of that answer is unknown. So you have to convert these to a convenient form. Okay. Now, since we are dealing with very small masses, we'll first find out how much is the energy associated with a mass of one atomic mass unit. If you know what is the energy associated with one AMU, then you can tell what is the energy associated with any number of AMU. Okay. Do these calculations first. You know from Einstein's mass energy equivalence that E is equal to mc square. First calculate what is the energy associated, or tell me this directly, what is the energy associated with 1 kg of mass? How much energy is present in 1 kg of mass? Or I should not say how much energy is present. How much energy is equivalent to 1 kg of mass? Yeah. Answer this directly. In place of m, you put 1. It's in SI units. You can substitute directly. And you know C is 3 into 10 power 8 meters per second. Square it. How much does it become? Okay. Mass is 1. C is close to 3 into 10 power 8. You square it. So the energy present in a mass of 1 kg is 9 into 10 power 16. And since we took mass and speed of light in SI units, you get energy also in SI units. 9 into 10 power 16 joules. Huge amount of energy. Okay. Fine. Next, how much is the energy equivalent to 1 AMU of mass? 1 AMU of mass is how much? 1.66 into 10 to the power of minus 27. 27 or 24? Very hard to remember these values. Per minus 27 kg. Okay. What is the energy equivalent to this mass? Directly substitute. It becomes 1.66 into 10 power minus 27 into c square, that is 9 into 10 power 16, and this answer will be in joules. Now 1.66 into 9, just a moment. Actually, you are supposed to do these calculations on your own. Do them once, you will remember them better. 14.94 into 10 power minus 27 and 10 power 16 becomes 10 power minus 11 joules. Okay, that is the energy associated with 1 AMU of mass. Okay, but expressing it in joules is inconvenient because in joules this is a very, very small value, 10 power minus 11 joules. A more convenient unit to express these energies is the electron volt. We had talked about electron volt in the last chapter or the chapter before that, dual nature. Okay, 1 electron volt is the energy gained by an electron when it passes through a potential difference of 1 volt. Okay, and it is equal to 1.6 into 10 power minus 19 joules. Compared to joules, electron volt is a very small unit. Okay, so you can say 1 joule is 1 by 1.6 into 10 power minus 19 electron volts. So if you express this energy in electron volts, it will become 14.94 into 10 power minus 11 divided by 1.6 into 10 power minus 19, and this will be in electron volts, and you simplify this, it will be close to 931.5 mega. Mega is a factor of 10 power 6 electron volts. That's the energy associated with 1 AMU of mass. Okay, you need to remember this. Usually in calculations, this is what we'll be using. 1 atomic mass unit corresponds to an energy of 931.5 mega electron volts. Okay, in terms of this, you can tell what is the binding energy of a nucleus and so on. Okay, just a moment, I'll give you one question. Okay, try this. Suppose the mass of 3Li7 nucleus is 0.042 U. U is atomic mass units, less than the sum of individual masses of its nucleons. Fine. We know that in the nucleus form, the mass will be less compared to sum of individual masses. So it is less by this much. So I want you to find out, first thing, the binding energy of this nucleus. Okay, answer has to be in mega electron volts or some in electron volts you give the answer. And then binding energy per nucleon also. Okay, fine. You can use calculator if you want. I'll give you all 2 minutes. Solve this quickly. I want answers from both of you. See, the mass of this nucleus is 0.042 atomic mass units less than the sum of masses of individual components. So this basically becomes the mass defect of this nucleus. And if you know mass defect, you can tell the binding energy. Simple. Binding energy is mass defect multiplied with c square. But you don't actually have to do this calculation because we have already calculated what is the mass equivalent to 1 atomic mass unit. Okay, 931.5 mega electron volts. Then for these many atomic mass units, 0.042, what is the, okay, wait, we have already calculated what is the energy equivalent to 1 atomic mass unit, 931.5 mega electron volts. So for these many atomic mass units, how much is the energy? Okay, so you can simply write it as mass defect in atomic mass units multiplied with 931.5 mega electron volts. Okay, this is how you calculate binding energies. So 0.042 multiplied with 931.5, and the answer would be in mega electron volts. Okay, you can do that calculation, that's fine. Next, binding energy per nucleon. Once you find the total binding energy per nucleon is simply binding energy divided by the number of nucleons. Number of nucleons is nothing but the mass number. Okay, the sum of number of protons plus number of neutrons. Okay, so that becomes the binding energy that you get here divided by how many nucleons does this nucleus have? 7. That will tell you binding energy per nucleon. Okay. Now you can say binding energy, okay, not you can say, we know that binding energy is the energy you need to supply to separate the constituents of a nucleus. Okay, to separate all the constituents of a nucleus. So you give that much energy to a nucleus, the protons, neutrons will have nothing to do with each other. They'll go off separate, independent. They'll become independent. So we can say that greater the binding energy, okay, means more the energy required to separate the constituents of the nucleus. You can say greater the stability of the nucleus. You may say like that. Okay, if a particular nucleus requires less energy to separate its protons and neutrons, it is less stable. If another nucleus requires a lot of energy to separate its protons and neutrons, it is more stable. You may say like that. But nuclear stability doesn't actually depend on its total binding energy. Okay, see, to separate all constituents, how much energy is needed is the binding energy. But how stable a nucleus is does not depend on the total binding energy of that nucleus. So basically what we are referring to when we say stability of a nucleus is, even if you remove, I mean, suppose you want to remove one of the constituents of this nucleus. Okay, how easy it is to do that. That is what we refer to, or that is what we are talking about when we talk about stability of a nucleus. Fine. So stability of a nucleus is measured in terms of how easy it is to pull out one nucleon, not how easy it is to break open the entire nucleus. Fine. So when it comes to stability of nucleus, binding energy is not the proper measure. Binding energy is the energy required to separate all the constituents of the nucleus. That is not what we mean when we say stability of a nucleus. Okay, how easy or difficult it is to pull out one of the nucleons is what we mean by stability of a nucleus, and that depends on binding energy per nucleon, how tightly each nucleon is bound. That is what gives you a measure of stability of the nucleus. Okay, depends on binding energy per nucleon. Okay, because when it comes to nuclei, stability itself means how difficult it is to remove one nucleon from it. Okay, not how difficult it is to separate all the nucleons. So obviously it depends on binding energy per nucleon. And it has been found that in nature, okay, nuclei having binding energy per nucleon greater than or equal to 8 mega electron volts. Okay, are stable. Means they stay like that unless disturbed by some very strong external forces. Okay, that nuclei stays as it is. If the binding energy per nucleon is less than 8 mega electron volts, the nuclei are found to be, those nuclei or such nuclei are found to be unstable. They tend to undergo fission reactions or fusion reactions on their own, okay, in order to attain stability. So you can determine the stability of a nucleus based on the binding energy per nucleon. Okay, those having 8 or above mega electron volts are found to be stable in nature. Less than 8 mega electrons or electron volts are found to be unstable. And there is a curve also, binding energy per nucleon. Scientists have determined how much is the binding energy per nucleon for all the available for all the nuclei that have been discovered so far. Okay, just a moment. Fine. So the binding energies and binding energies per nucleon for all the different nuclei that have been discovered so far are plotted on this graph. Now you can see, okay, there is a reference line here at 8 mega electron volts. Fine. And if you see the mass number, close to mass number 30, and on the other side, close to mass number 170. Okay, according to your textbook, the numbers are 30 and 170. Okay, the nuclei with mass numbers between 30 and 170, they have a binding energy per nucleon more than 8 mega electron volts. Okay, so these nuclei are stable in nature. Fine. Nuclei having mass number less than 30, their binding energy per nucleon is less than 8, they are unstable. Okay. Nuclei having mass numbers more than 170 also are unstable. Fine. Now, nuclei having mass numbers less than 30, these are called light nuclei. Okay, in terms of mass, they are very light. And nuclei with mass number more than 170, they are called heavy nuclei. Okay. Now, what is the problem with light nuclei? Their mass number is too low. So what light nuclei tend to do is they tend to combine, they tend to fuse to become a heavier nucleus. Okay. So light nuclei, okay, tend to undergo fusion reactions. So when two light nuclei fuse, means they combine to become a heavier nucleus, the mass number increases. And if mass number increases, means two light nuclei combine, they form a new nucleus whose mass number is more. And the new nucleus whose mass number is more will be relatively more stable compared to the individual light nuclei. Okay, so they tend to undergo fusion reactions to attain stability. And heavy nuclei, on the other hand, what is their problem? Their problem is that the mass number is too high. Okay, so what they will do is they will separate, they will split into smaller nuclei with lesser mass numbers. Okay, splitting into smaller nuclei is called fission. So heavy nuclei tend to undergo fission reactions, okay, where they disintegrate into smaller nuclei. If a heavy nucleus disintegrates into a smaller, into two or more smaller nuclei, then those smaller nuclei that form will have lesser mass number. Lesser mass number will bring them towards stability. So the daughter nuclei that form, or the fragment nuclear fragments that form, will be more stable compared to the original heavy nucleus. Okay. Fission reactions are what you see in stars. Stars give us energy. Okay, the sun and other stars, they release energy from these. Uh, what did I say? Did I say fission? Fusion. Okay, fusion reactions are what you see in stars. Okay, they give energy from fusion reactions. And fission is what you see in nuclear reactors. Okay, Nuclear reactors are man-made, obviously. It is easy, I mean, relatively. Relatively, it is easy to make a fission reaction happen than a fusion reaction. Okay. Why is nuclear fusion difficult? Nuclear fusion means two nuclei combining to become a single nucleus. Okay. You consider hydrogen itself. What is there in the nucleus of hydrogen? One proton is there. Now, if two hydrogen nuclei have to fuse, okay, what should happen is a proton and another proton should come very close to each other in order to fuse. But proton-proton being positively charged entities, they'll experience electrostatic repulsion. So it is very difficult to bring them to such close distances where they can fuse. Now, how close a distance do you have to take them? You know what is the size of a nucleus, no? R naught into a power 1 by 3, where R naught is 1.2 into 10 power minus 15 meters. So the size of a nucleus in which protons and neutrons stay together, okay, the distance in which protons and neutrons stay together is approximately this much, 10 power minus 15 meters. So if you want to fuse two nuclei and make them a single nucleus, you will have to bring the nuclei to such small distances from each other. Okay, you will have to take them to distances of the order of 10 power minus 15 meters. And like consider the charges of protons, 1.6 into, or not charges actually, you should consider energies. Fine. Now protons are charged particles. Let's say they have charges E and E. E is 1.6 into 10 power minus 19. This also has 1.6 into 10 power minus 19. Initially, let's say they are very far from each other. Now, the potential energy, electrostatic potential energy between two charges is given by the formula K Q1 Q2 divided by R, where R is the separation between them. Fine. Now, if you want to fuse these two nuclei, you have to bring them to a distance of 10 power minus 15 meters. Now, initially, when they are far from each other, the potential energy tends to 0. Okay. So initial potential energy tends to 0. Let it be. But when you want to fuse them, you have to bring them to very close distance. Then the final potential energy will be K. K is 9 into 10 power 9. Q1, Q2, the charges of two protons, you'll have to multiply them. Divided by the distance to which you want to bring, 10 power minus 15 meters. Now this will be significant. Okay, it's still a small number. For one proton, it is a small number. But if you consider a huge mass, then it becomes a significant amount of energy that you need to supply. For example, let's say 1 mole of hydrogen atoms you want to fuse, or 1 mole of hydrogen nuclei you want to fuse. 1 mole has how many nuclei? 6.023 into 10 power 23 nuclei. So if you want to give sufficient energy to fuse 1 mole of hydrogen nuclei, you will have to give an energy of this into 6 into 10 power 23. 1 mole is just 1 gram of hydrogen. To fuse 1 gram of hydrogen, first you have to supply this much energy to bring the nuclei together. Okay. And yeah, very recently it has been achieved. Very, very recently, last year, in fact, it has been achieved. They have done fusion reactions in the lab. Okay. But usually to supply this much energy is very difficult. Okay. That's why we don't carry out fusion reactions practically. They happen in nature. On stars they happen. Okay. Or in stars they happen. Okay. Why? How can they happen in stars? Because stars are already at such high temperatures. High temperature means high energy. The nuclei, let's say there are two hydrogen nuclei. Fine. Temperature is high means they are moving very fast. They have a lot of kinetic energy. Okay, the nuclei are moving very fast. Then it's possible that the hydrogen nuclei come so close to each other that they fuse. So in stars, for such high temperature, at such high temperatures, such high kinetic energies, it's possible. Fusion is possible. And when they fuse, they'll release more energy. See, this is the energy you need to give to fuse these nuclei. But once they get fused, they'll give you out, they'll in like reciprocation, they'll give you more energy than what you spent. Okay, so you can extract energy from fusion process, but if you want to practically do it, you will initially have to supply a lot of energy. That is difficult to do. Okay, but in fission, what you have to do, you have to take a heavy nucleus and somehow break it open. Okay, that is easier. That process also requires a little bit of energy to be given initially, and you will get more energy in return. Okay, but that is relatively easier to do compared to fusion. Okay, we'll discuss this in further detail later. Let's quickly talk about nuclear force. We know that protons and neutrons are held inside the nucleus. Okay, now the nucleus is not a closed ball or something like that. Okay, it's just a space inside which protons and neutrons are present in a stable form. They don't want to separate from each other. Okay, now we know protons, being like charges, will be experiencing electrostatic repulsion, but inside the nucleus they stay there. Okay, it's not like they're closed in a shell or something. Fine, at such small distances of about 10 power minus 15 meters, or a small multiple of that 10 power minus 15 meters, in such small distance, proton will stay together on their own. Okay, so there must be a force, or okay, we know it's nuclear force, so there's no point talking about some force. So you can say that nuclear force, the force that acts between protons, neutrons, and also neutrons. Okay, the force that acts between nucleons when they are at such short distances from each other. Okay, that is what is nuclear force, and it is much stronger than electrostatic force. Okay, the protons will be experiencing electrostatic repulsion, but they are still happily staying inside the nucleus, means the nuclear force is stronger than the electrostatic force. Okay, so nuclear force is way stronger than electrostatic force. Next, nuclear force is independent of charge. It will act between protons. It will act between a proton and a neutron. Neutron is neutral, you know that. It also acts between neutrons. So it is independent. So it is independent of charge. Any nucleons, be it neutron, proton, or proton, if they come to such short distances from each other, they will experience nuclear force. It will bind them together. Okay. Next, nuclear force can be attractive. It can even be repulsive. Depending on how close the nucleons are. So it depends. Distance between the nuclei. Sorry, nucleons. Now, how much distance? If the distance between the nucleons is less than 0.8 femtometers, then the force is repulsive. If the distance between the nucleons is greater than this, then it is attractive. Now, the everyday distances that we come across are usually greater than 0.8 for me, right? Does that mean nuclear forces attract everything in everyday life? No. Just a moment. So the everyday distances that we come across are definitely greater than 0.8 for me. That doesn't mean nuclear forces will be attracting everything in the universe. Okay. If that is true, then all the mass of the universe should have stayed together. there is a range up to which nuclear force acts. Okay, a few Fermi only, not beyond that. So greater than 0.8 Fermi up to a few Fermi, few femtometers, nuclear force will act and it will be attractive in nature. Beyond the distance of few femtometers, nuclear force won't even act. Okay. We will talk more about range of a nuclear force in the next class. But just remember that it can be repulsive as well as attractive. Okay. Fine. We'll continue in the next class. Next class, we'll talk about nuclear force in detail and how to calculate energy released in nuclear fission and fusion reactions. Fine. Radioactivity, right now, it is not part of JEE main syllabus. It is there for JEE advanced. So we won't be talking about radioactivity right now. We'll only discuss energy released in nuclear reactions. Okay. Thank you all. We'll continue in the next class.